Hello, everyone. Today I'd like to tell you about one interesting thing. Have you ever wondered that inside an ordinary pencil hides a Nobel Prize and a technology that will change your smartphone, your clothes, and perhaps the entire future of humanity? Graphene is a truly amazing material, often called the material of the future. Let us consider the physico-chemical mechanisms that provide graphene with its unique properties. At the heart of each of them lies the specific hybridization of carbon atoms and quantum mechanical effects. Here are 5 impressive facts about it. Graphene is the thinnest and strongest material in the universe. Imagine that every carbon atom is a construction set piece with 3 very powerful arms. With these arms, the atoms grip their neighbors tightly, forming an ideal flat grid of hexagons similar to a honeycomb. These bonds between atoms, called sigma bonds in chemistry, are among the strongest known in nature. Because the grid is flat and regular, any load is distributed across the entire plane instantly and uniformly. Why is graphene flat? Atoms in this configuration simply have no free arms left to build bonds upward or downward. Therefore, graphene always remains a sheet just one atom thick. Interestingly, it is precisely this flat nature of graphene that serves as the foundation for an entire family of nanocarbon materials. If we imagine graphene as a sheet of paper, then all other forms are the result of how we fold or roll that sheet. The second impressive fact is the high electrical conductivity of graphene. Although 3 arms of the atom are busy forming the graphene two-dimensional framework, each atom has a 4th arm, an electron, that points up and down. All these free electrons combine into a common cloud above and below the graphene sheet. Inside this cloud, electrons can fly almost unimpeded and at tremendous speeds. This makes graphene a better conductor than even copper. Another interesting fact is that graphene can be considered almost transparent. In physics, transparency is the ability of a material to allow electromagnetic waves, particularly visible light, to pass through it without significant absorption or scattering. A sheet of graphene absorbs only about 2.3% of incident light. It is so thin that photons simply do not have time to interact with it. The 4th property in order is the barrier quality of graphene. It creates a paradoxical situation where it is transparent to light but impermeable even to the smallest gas atoms. Graphene acts as an absolute physical barrier, whose dense electronic field at the centers of the hexagonal cells reliably repels any atoms and molecules of gases, including ultra-small helium. However, the material makes a unique exception for hydrogen due to the mechanism of catalytic dissociation on natural surface folds. Upon hitting such lattice defects, a hydrogen molecule breaks into individual atoms and gives up its electron to the general conduction network of graphene, turning into a proton. Since the graphene film has an anomalously high permeability specifically for protons, they freely jump to the opposite side of the material, where they recover to their original state, which turns graphene into an ideal selective filter. The 5th interesting fact is that graphene was first obtained by scientists using ordinary adhesive tape. For this discovery, they were even awarded the Nobel Prize in 2010. The secret of graphene lies in the different strength of the bonds within graphite. Imagine graphite as a stack of paper. The sheets inside are very strong, but they are hardly glued to each other. Ordinary tape easily overcomes this weak attraction and separates the layers. At the same time, the graphene layer itself is so strong that it does not tear, allowing for a pure sheet only 1 atom thick. In addition to classic single-layer graphene, science and industry actively use other configurations of nanocarbon. If we consider graphene as a basic building sheet, it can be packed or modified in various ways. For example, in the form of carbon nanotubes. Imagine that you rolled a sheet of graphene into an ideal seamless cylinder. The atoms are still connected by 3 arms in the plane of the sheet, but now that plane is curved into a circle. The wall of such a tube is still just 1 atom thick. Due to this shape, nanotubes possess incredible tensile strength and can function as superconducting channels for electrons. Another popular material is fullerenes. If a few pentagons are added to the hexagonal grid of graphene, the sheet begins to bend until it closes into a sphere. The most famous is C60, which looks like a soccer ball. The sphere is hollow inside, and its shell is a layer 1 atom thick. Due to their shape, fullerenes can pack other atoms or medicines inside themselves, acting as nanocapsules. Another type of carbon material is carbon nano-onions, CNOs, which we will discuss further. These are structures that most resemble a matryoshka doll. They consist of several fullerenes of different diameters nested inside one another. These are concentric spheres where each individual sphere in this onion is a closed monolayer of carbon. Between the layers, the same weak forces act as in ordinary natural graphite, which is often used as pencil lead. Weak forces hold the layers together, but inside each individual layer is a super strong bond, identical to that in regular single-layer graphene. In conclusion, thanks to its extreme properties, record strength, conductivity, and chemical resistance, graphene finds application in almost all high-tech industries. Graphene is used as nano-reinforcement to strengthen other materials, and its unique structure allows for the creation of ideal filters. Graphene lacquers protect metals from rust much more effectively than traditional coatings. Thanks to its transparency and elasticity, graphene is ideal for creating foldable smartphones and smart clothing. This is by no means a complete list of the areas in which carbon nanostructures are capable of achieving a true technological breakthrough. Stay with me. It's going to be very interesting.